to the conveners for your kind invitation, and I hope you will enjoy the talk.
Sure.
Okay, so the title is related to physical heights. I will talk about physical heights, and I will focus on, namely on normal heights. Physical heights, this is a very geodetic topic, so maybe you ask yourself why I should talk about this issue here at the EGU. So I will start my talk with the motivation. Last year in June at the Hotel Marossi Symposium in Milan, heights and height system were discussed. Hotel Marossi Symposia are focused on mathematical or theoretical geodesy. We discuss usually different topics from geodetic theory, and last year we discussed heights, physical heights namely, and the two basic concepts of physical geodesy, namely the geoid and quasi-geoid. It's a very old issue, and I would not like to advocate any of these two concepts, but I would like to say a few words about normal heights and maybe to recall some issues which are related to the definition of normal heights and namely to their correct application. The discussion at the Hotel Marossi Symposium actually resulted in a proposal of a motion. This motion was proposed at the plenary of the symposium at the end. The motion could be summarized very easily, actually in maybe one sentence, and that would be: do not use the quasi-geoid as a height reference surface for normal heights or any other physical heights in geodesy. So that's basically the topic of my talk. The motion was not accepted, there was no formal vote, but at the end we decided or we agreed that we will continue in this discussion within the geodetic community with experts in the field, and that's basically the main reason why I'm here today. The presentation is a compilation of thoughts of different people, and as always it's some kind of what you will see, it's an agreement between my view and Fernando's view, so that's important also to say. Okay, so what's the issue about normal heights? As we all know, normal heights were introduced roughly in the middle of the last century. They were supposed to represent an alternative to the classical height system, which is represented by the geoid and orthometric heights. The reason why they were introduced, I think it's very well known. Orthometric heights have some issues, namely with their estimation, because no matter what kind of data we use, at the end we have to adopt some kind of hypothesis about the topo mass density distribution. And as the mass density distribution is not known, then this alternative concept was introduced. It was actually adopted in some countries, first in Eastern Europe, but as they were proposed roughly at the same time by Russian geodesists, namely by Molodyansky, and by French geodesist Vignal. They were also introduced in France, but as you will see, they are also used in other countries since. Normal heights underwent some development. There is obviously not a single definition which could be found in the geodetic textbooks, and possible definitions include they differ in the way how the height reference surface is defined. You can find references where the reference ellipsoid is used as a height reference surface, or the quasi-geoid, and eventually also the geoid. They differ also in geodesics that they use, and they also differ in metrics. I just did some survey on the internet, and there are a few selected quotes, and I apologize to all these authors, because of course these quotes are taken out of the context. But just you can see clearly that there is no single definition all authors would agree on. Usually normal heights are related to the quasi-geoid model. So countries which use normal heights in practice, they usually estimate a local or regional quasi-geoid model, which is then used for the height transformation. If we want to estimate normal heights from GNSS data, then usually the local quasi-geoid is estimated and used. Okay, for heights, for physical heights, we need some basic definitions. I guess we all know this. I will not go into the details. We need the potential, we need the potential gradient, equipotential surface, and so on. Geoid, of course, and the quasi-geoid. And plumb lines, these I think these are the basic definitions. And of course, the normal gravity field for normal heights, very important. And the concept of the disturbing field, because this is actually the essence of the physical heights. The geoid height or height anomaly actually represent, in the geometric sense, the difference between the real field and the normal field. Okay, I just a short remark on geometry of the different plumb lines. Physical heights use different plumb lines. They are related to two different gravity fields. Orthometric heights are related to the real gravity field, and normal heights are related to the normal gravity field. They are two different plumb lines, but and of course we also have the ellipsoidal normal. But if you do some investigation how these plumb lines, how the length of the different plumb lines differ, so they actually the differences are very, very small, so they can be even interchanged, which often happens. For example, the normal plumb line is replaced or approximated by the ellipsoidal normal. Okay, so coming to the height systems in geodesy. So there are basically two different types. We have geometric heights and we have geometric height system, which is basically the height system related to the reference ellipsoid. If we can compute Cartesian coordinates in some global reference frame, by transformation of the Cartesian coordinates, we can get the geodetic coordinates, or the ellipsoidal coordinates as they are called sometimes, and one component of these coordinates is the geodetic height. Geodetic height as the length of the ellipsoidal normal from the reference ellipsoid to the point of interest. And of course, geometric heights are okay, they can be of course used, but they have one major flaw, and that's that they don't consider in any way the gravity field effects. So they are not very useful in practice in many practical applications, because they really don't consider the gravity field effects. So that's why we have the physical heights and physical height systems, and there are two major types: the classical concept based on the geoid and the orthometric heights. And then, well, modern height system, as it used to be called, at least back in the 60s, which is based on the normal heights. And here I use for the first time also the geoid. So actually, if you look at these two height concepts, they are based on the same height reference surface, but they just use different heights. Of course, they will differ, as we will see. Of course, the realization of the height reference surface, I will skip that. The datum can be realized in many different ways. Maybe this figure is interesting. On your left-hand side, you see the very well-known picture produced by BKG in Germany, where you can see the countries in Europe which are using the normal height system. These countries are in red. And of course, we also have countries which are using the orthometric heights, and of course, we also have countries which are using other kinds of physical heights, like, for example, normal orthometric heights, or even there are countries that are using leveled heights without any gravity field effect corrections. So the situation is not very easy in this respect. Both height systems are used even on the same continent. Okay, so physical heights, which is the main topic of my talk, there are three major groups, but I will not talk about dynamic heights, which would be perfect. They really give the precise information what is up and what is below in respect of the gravity field effects, but they are not used in practice for different reasons. I will focus namely on arithmetic and then normal heights. Okay, before I get to the physical heights, I shortly mentioned the geodetic heights, which I already introduced, the height of a point of interest above the reference web. So this is, I think, a simple concept. Okay, before any physical heights are introduced, I have to mention the geopotential numbers, because all the definitions of all physical heights are based on the geopotential number. The geopotential numbers are defined as the difference of the potential values between 2 points. So if Wg is the potential at the geoid, then if I have point A, based on the sign of this difference, I can either say what is actually above or what is below the geoid, reflecting the gravity field, the real gravity field of the Earth. Geopotential numbers can be, of course, estimated if I would level and measure gravity at the same time. I could also use other techniques like chronogeodesy, for example. If I use atomic clocks, these differences could be eventually measured. Okay, and dynamic heights, I say, okay, I will not talk about dynamic heights. Automatic heights, the classical height system, they are defined through the geopotential number, and the geopotential number is metricized by the value of, by the mean value of real gravity. The mean value is considered along the plumb line between the geoid and the point A, and this is actually the weak point or the disadvantage of automatic heights, because I cannot measure gravity inside topography. I cannot even calculate gravity inside topography, not accurately maybe enough. So some kind of approximation must be introduced here. We have to make some assumption about mass density within topographic masses. And based on the approximation, we get to different automatic heights here. For example, as an example, is the definition introduced by Helmert, which is based on the Poincare gravity gradient and some adopted mean value of topo mass density. Okay, well, the geometry of automatic heights is of course complex as it is the gravity field, and now well, normal heights, which is actually the topic of my talk. So normal heights were introduced by roughly at the same time by Molodensky and the Russian geodesist and French geodesist Vignal. The idea is relatively simple. If we don't know the gravity, the real gravity inside the topographic masses, let's replace it by something what can be estimated easier or without any hypothesis. And Molodensky basically used this definition when he replaced real gravity by normal gravity. Normal gravity generated by the reference ellipsoid, of course, is known analytically at any point. So the mean value of normal gravity can be computed up to whatever accuracy we may require. Based on this definition, it is quite clear that the height reference surface to which these heights refer is also the geoid. And so actually we have to compute the mean value of normal gravity between the geoid and the point of interest. There are actually more possible definitions of normal heights. The first equation, it's the one which was used on the previous slide. Basically here we can see the approximation. We replace the vertical gradient of real gravity potential along the plumb line, along the real plumb line, by the vertical gradient of the normal potential. of course, when we change these two terms, we have to also change the heights to keep the equation. But it is obvious that this definition is just it just approximates the definition of orthometric heights. In the definition 2, which is in the second equation, basically we can define normal heights by mapping the whole problem from the real space to the normal gravity field space. And we replace the real potential by the normal potential. We replace the geoid by the reference ellipsoid as the reference equipotential surface of the normal field. We replace point A by the point A primed, which is actually the point for the surface point. It's the point at the telluride. This condition here must be A primed is actually defined through this condition here. And we also replace, of course, the real plumb line by the normal plumb line, and the normal height is replacing the orthometric height. So these two definitions, if you compare these two equations, are basically identical. The only difference is that, of course, in the first equation here, we evaluate this value along the plumb line between the geoid and the point of interest. And here we are actually moving along the normal plumb line between the reference ellipsoid and the point A primed. The values, remaining values, are actually the same in these two equations, because this normal potential at the point A primed is equal to the real potential at the point A, and the normal potential at the ellipsoid is equal to, by definition, to the real potential at the geoid. If we compare directly the definitions of orthometric and normal heights, that we get this relation, the first equation, where we can see clearly the difference in the different, that these heights are using different metrics. These two heights can be even transformed from one to the other, when we would know, of course, these two values here. And of course, namely this value here is problematic. But we don't have to worry too much about the different metrics, because both orthometric and normal heights can be realized through observations which take care for the different metrics. Right. Okay, normal orthometric heights, I will skip that one. Now, what is important? If we study the relationship, the geometric relationship between the points A and A primed, that would be for a surface point, it would be the point at the telluride, we can easily find out that the separation is given by this term here, the so-called height anomaly, which can be computed as a disturbing potential at the point A divided by normal gravity at the point A prime. This value is no problem to compute, but we have to compute the disturbing potential. If we are at the surface, the disturbing potential at the surface can be computed using surface gravity, for example, or by combination of the global model and local surface gravity data, solving, for example, the geodetic boundary value problem, the Molodyansky problem. But if we are at any other point, if we are above the surface or below, then we have to remember that we have to compute the disturbing potential at any new point, no matter if we are at the same ellipsoid or normal. So if we are moving from the surface, for example, if we would like to compute the normal height of an aircraft, then we would have to compute the disturbing potential at the aircraft. Not to use the same height anomaly computed from surface data for any other location. We would have to really recompute the height anomaly for any new point. That's somehow inconvenient if you think about this concept, because for geoid we don't have this. We compute the geoid once and we can use it for any point or any location you can think of, above, at, below the surface. So there is another issue. geodesists like to put the height anomaly above the reference ellipsoid. Then of course you can get another surface which is called the quasi-geoid, and then people like to think about the normal height as the height of a point above the quasi-geoid. And this is very often what happens. I mentioned that already at the beginning, but if you think about the quasi-geoid as a height reference surface, it has some features which do not really qualify this surface to be a meaningful height reference surface, and the main issues are maybe listed here. Quasi-geoid, first of all, doesn't have any physical meaning, so this is a little bit inconvenient for a height reference surface of physical heights. Quasi-geoid is much rougher than the geoid. This is very well known. This makes it a little bit inconvenient if you have a quasi-geoid model and you would like to interpolate your quasi-geoid, your height anomaly to any general location, for example. This roughness is caused by the fact that the quasi-geoid reflects or mirrors the features of topography. So, for example, if topography folds, even the quasi-geoid can fold, which is really inconvenient. And last but not least, as I mentioned already, if I consider the quasi-geoid as a height reference surface, I cannot use it for any location. It can be maybe good for surface points. Okay, we are usually interested in heights of surface points, but if I would like to compute the normal height of any other point, this transformation would not be valid. Okay, roughness of the quasi-geoid, just to show you some numerical results. We evaluated the roughness of the geoid and the quasi-geoid as the horizontal inclination, and we have here two formulas, the inclination of the quasi-geoid and the inclination of the geoid. Okay, I don't want to go into the details, but basically if you compare these two formulas, you see that they are almost the same, but they differ by this term here. So when I compute the horizontal inclination of the quasi-geoid, it depends on the inclination of the topography. And if you think about the topography, for example the Alps, it's quite obvious that the inclination of the quasi-geoid, or the roughness of the quasi-geoid, must be much larger than the one of the geoid. And this is basically, this figure shows the numerical results computed for some small test area in the Alps. So the numerical values are not important, but you see how much this is, what you can see here is the stem here. That would be the inclination of the topography, and that maps directly into the inclination of the quasi-geoid. So if you have such a height reference surface and you would like to interpolate some value in this surface, then this is really difficult. Okay, we don't see any folds here or any other problems, but this is mainly because the topography which was used was already regularized or smooth. Yes. Okay, estimation of height is a very important issue. So there are different methods, but okay, GNSS positioning and leveling. Namely, GNSS positioning is important. I will skip leveling. We all know this holonomicity problem and the different corrections which must be applied. But let's look at the relationship between orthometric heights and geodetic heights. That would be this equation here. So for this transformation, we need to know the geoid. Of course, to estimate the geoid is not that simple, but once we have the geoid, we can use this equation for any point at any location. Still, this value here would be the same. If we look at the equation for normal heights, then again we have the geodetic height and we apply the corresponding correction. But in this case, this value here depends on the position of the point which we try to position vertically. So if I have any new point, even along the same normal, I have to always recompute the value of the height anomaly. A little bit inconvenient. Right, this is basically summarizing what I just said. That if zeta, this term here, would be the value represented by a local quasi-geoid model, then this height transformation could be used only for surface points, not for any other point. Right, okay, and let me move to the summary of my talk. So basically my presentation was meant to support this motion we discussed at the Hotemaros Symposium. The main message is do not use the quasi-geoid as a height reference surface. It can be quite inconvenient for people who are using normal heights and they are used to the quasi-geoid models. But really what should be used instead is the height anomaly. Someone can say, okay, it's basically the same, but as I tried to prove, it's actually not. If we are interested in height of any point, not only of surface points, then this is not the same. The quasi-geoid, besides this issue, has many unpleasant features which should not, do not really qualify the quasi-geoid as a meaningful or clever height reference surface. Normal heights, of course, can be used. I don't want to say anything against the normal heights. If anyone is happy about the normal heights, please use it. They can be estimated by leveling or by GNSS if you apply the correct height anomaly, of course. But anyway, last comment maybe here. It's maybe something what Fernando would not agree, but maybe after so many years of using normal heights, maybe the time came to the point when normal heights, as the approximation of the autometric heights, could be eventually reintroduced, or even in countries which are not using autometric heights. But this is my personal opinion. Okay, and at the end, one funny slide. A few days ago, I received a message from Marcelo. Actually, he tried to chat with GPT, right, about this issue.
That's right.
So he asked some controversial question, right, about the geoid and quasi-geoid. So I tried also by myself. I never tried to chat GPT before, but so what does the artificial intelligence think about this issue? So I asked this question, okay, are automatic heights superior to normal heights? Maybe a controversial question for some of you. And the answer is quite interesting, actually. It's the same along the lines Marcelo received. So actually the artificial intelligence is not that stupid. Maybe the answer is not completely accurate, but okay, the answer is actually, okay, both heights have their advantages and disadvantages, okay, very general statement, but autometric heights, according to this, provide better representation
so our papers are being read.
Yeah, it's a compilation of different, of course, you are absolutely right, it's a compilation of different thoughts in different papers, so not surprising, the answer is not that surprising, but it somehow reflects also the content of my talk. So I hope that the artificial intelligence will not take over. That the ideas are coming from people. Still, as a compilation of the different ideas which can be found, it's not that bad, I would say. So thank you very much. And now, if you have any question, I would be happy to answer.
Thanks.